Now that we've derived formulas for the least squares estimators of the beta parameters in the simple linear regression model, we're in a position to determine some important characteristics of their sampling distributions. This is important because in order to develop inference procedures for the beta parameters, we need information about how their least squares estimators behave as random variables, and that behavior is contained in the sampling distributions of those estimators. In this video, we'll look at characteristics of the marginal distributions of both beta 0 hat and beta 1 hat, as well as characteristics of their joint distribution. This will provide the foundation for computing probabilities involving beta 0 hat, beta 1 hat, and linear combinations of beta 0 hat and beta 1 hat, and ultimately to the development of inference procedures for the parameters beta 0 and beta 1, including the development of hypothesis tests and procedures for the construction of confidence intervals. So here's an outline of what we'll be looking at in this lecture. We'll first look at characteristics of the marginal sampling distribution of beta 1 hat. We'll see how to re-express beta 1 hat as a linear combination of the responses. Once we've done that, we'll be able to derive the mean of the marginal sampling distribution of beta 1 hat. We'll then derive formulas for the variance and standard deviation of the marginal sampling distribution of beta 1 hat. We'll then look at characteristics of the sampling distribution of the standardized version of beta 1 hat. We'll then look at characteristics of the marginal sampling distribution of beta 0 hat. We'll first look at how to re-express beta 0 hat as a linear combination of the responses. Once we've done that, we'll be able to derive the mean of the marginal sampling distribution of beta 0 hat. We'll then derive formulas for the variance and the standard deviation of the marginal sampling distribution of beta 0 hat. And then we'll finally look at the characteristics of the sampling distribution of the standardized version of beta 0 hat. And then finally, we'll look at characteristics of their joint sampling distribution. In particular, we'll derive a formula for the covariance of beta 0 hat and beta 1 hat, and also a formula for the correlation of beta 0 hat and beta 1 hat. So let's first look at characteristics of the marginal sampling distribution of beta 1 hat. Recall that the formula for the least squares estimator of beta 1 is given by beta 1 hat equal to s sub xy divided by s sub xx, where s sub xy is the corrected sum of products of the x's and the y's, and s sub xx is the corrected sum of squares of the x's. This formula for beta 1 hat can be re-expressed in the algebraically equivalent way beta 1 hat equal to the sum, I going from 1 to n, of the products c sub I times the response variable y sub I, where these constants c sub I are equal to x sub I minus x bar divided by s sub xx. And so from this representation, we see that beta 1 hat is a linear combination of the responses for all experimental units in the data set. Next, we're going to derive the mean of the marginal sampling distribution of beta 1 hat. Using the linearity property of the expectation operator, it's easy to see that the mean of the sampling distribution of beta 1 hat, which is denoted by mu sub beta 1 hat, which is also the expected value of beta 1 hat, is equal to the expected value of the sum, I going from 1 to n, of the c sub I values times the y sub I values. And by the linearity property of the expectation operator, that's equal to the sum I going from 1 to n of the product of c sub I times the expected value of y sub I. Applying the linearity of the expectation operator to y sub I itself, so the expected value of y sub I turns out to be equal to beta 0 plus beta 1 times x sub I. And so if we substitute that expression into the formula, the sum for the involving expected value of y sub I in the formula on the top of the slide, we see that the mean of the sampling distribution of beta 1 hat turns out to be beta 0 times the sum of the c's plus beta 1 times the sum of the products c sub I times x sub I. It is straightforward to show that the c values add up to 0, and the sum of the products c sub I times x sub I is equal to 1. And so from that, we can determine that the mean of the sampling distribution of beta 1 hat, mu sub beta 1 hat, is equal to beta 1. So in words, this states that the mean of the sampling distribution of beta 1 hat is beta 1 itself. This implies that the least squares estimator, beta 1 hat, is an unbiased estimator of the slope coefficient beta 1. Thinking graphically, this tells us that the sampling distribution of beta 1 hat is centered at beta 1. Next, let's derive formulas for the variance and standard deviation of the marginal sampling distribution of beta 1 hat. A very important assumption underlying the simple linear regression model, which therefore underlies the development of analysis procedures for that model, is the assumption that the error terms, the epsilon sub i's, I going from 1 to n, are stochastically independent. This implies that the covariance between every pair of error terms is 0. These results, in turn, imply that the response variables for different experimental units are stochastically independent and pairwise uncorrelated as well. Using this fact, along with properties of variance, the variance of beta 1 hat can be found, and we denote the variance of beta 1 hat in a couple different ways. So sigma squared sub beta 1 hat, and also var of beta 1 hat for variance. And so beta 1 hat, we know, can be expressed as the sum I going from 1 to n of the products c sub I times y sub I. And so the variance of beta 1 hat is equal to the variance of that linear combination of the response variables. Now, because the response variables are uncorrelated, using that fact along with the properties of variance that we looked at in Module 1, this is equal to the sum I going from 1 to n of the variance of c sub I times y sub I. Now, we can pull the c out of that expression, out of the variance expression, but remember we have to square that c value. And so the variance of beta 1 hat is given by the sum I going from 1 to n of the products of the squared c values times the variance of the y values. Now, another important assumption is that the error terms all have the same variance. What that means is that the variance of epsilon sub I, which we could denote by sigma squared sub I, because the error variances are all the same, we can remove that subscript on sigma squared, and so we'll just denote that common value of the variance by sigma squared. And so the variance of y sub I, again using properties of variance, is equal to the variance of the error terms. So variance of y sub I is equal to the variance of epsilon sub I, and because of this underlying assumption, that is equal to sigma squared for each I going from 1 to n. And so from this, if we plug those values or that value back into the expression on the previous slide, we see that the variance of beta 1 hat is equal to sigma squared times the sum of the squared c values. It's straightforward to show, and I recommend that you do this as a practice problem, that the sum of the squared c value is equal to 1 over s sub xx, where s sub xx is the uncorrected sum of squares of the x values. So plugging that back into the formula, we see that the variance of the marginal sampling distribution of beta 1 hat is equal to sigma squared, which is the variance of the error term, divided by s sub xx. The standard error of beta 1 hat, that is, the standard deviation of the sampling distribution of beta 1 hat, is the square root of this expression. We will denote the standard error of beta 1 hat by sigma sub beta 1 hat, and also by SD for standard deviation of beta 1 hat. And that's equal to the square root of sigma squared divided by s sub xx, the uncorrected sum of squares of the x's. So putting this all together, all these results on the same slide. In summary, the mean, variance, and standard deviation of the sampling distribution of beta 1 hat are as follows. So mu sub beta 1 hat, the mean of the sampling distribution of beta 1 hat, is equal to beta 1 itself. And again, that implies then that beta 1 hat is an unbiased estimator of beta 1, and that's a good property for an estimator to have. The variance of beta 1 hat, sigma squared sub beta 1 hat, is equal to the ratio of the variance of the error terms divided by the uncorrected sum of squares of the x's. And the standard error of beta 1 hat, which is the same as the standard deviation of the sampling distribution of beta 1 hat, is equal to the square root of sigma squared over s sub xx. Next, let's look at characteristics of the sampling distribution of the standardized version of beta 1 hat. Denote by z sub beta 1 hat the standardized version of beta 1 hat. In other words, z sub beta 1 hat is equal to the ratio of beta 1 hat minus the mean of its sampling distribution divided by the square root of sigma squared sub beta 1 hat. And so we're dividing the difference between the estimator and its expected value. We're dividing that difference by the standard error of beta 1 hat. And that is equal to beta 1 hat minus beta 1 all over the square root of sigma squared over s sub xx. And so once we have standardized a random variable, you'll recall that the random variable has a mean of 0 and a variance of 1. And because the variance is equal to 1, the standard deviation is equal to 1 as well. And that's what we have here. The mean, variance, and standard deviation of the standardized version of beta 1 hat are as given below. And I see I have a little typo here. So we should have z sub beta 1 hat there in that line. So the mean of z sub beta 1 hat is equal to 0. The variance of the standardized version of beta 1 hat is equal to 1. And the standard deviation of the sampling distribution of the standardized version of beta 1 hat is equal to 1 as well. All right, next, let's look at characteristics of the marginal sampling distribution of beta 0 hat. Recall that the formula for the least squares estimator of beta 0, which is denoted by beta 0 hat, is equal to y bar minus the product beta 1 hat times x bar. This formula for beta 0 hat can be re-expressed using the algebraic equivalent expression beta 0 hat equal to the sum I going from 1 to n of b sub I times y sub I, where b sub I is equal to the expression shown here, and I've actually got two expressions that we can use to represent b sub I. So the first one is b sub I equal to 1 over n minus the quantity x sub I minus x bar times the quantity x bar over s sub xx. and that is algebraically equivalent to 1 over n times the sum of the squared x values minus x bar times x sub I divided by s sub xx. Now from this representation, we see that beta 0 hat is a linear combination of the responses. Now that we have this linear representation of beta 0 hat, we can derive the mean of the marginal sampling distribution of beta 0 hat from that representation. And so using the linearity property of the expectation operator, the mean of the sampling distribution of beta 0 hat, which we will denote by mu sub beta 0 hat, for the mean of the sampling distribution of beta 0 hat, we'll also denote that as the expected value of beta 0 hat because they're the same quantity. And so that is equal to, by the linearity property of the expectation operator, the sum, I going from 1 to n, of b sub I times the expected value of y sub I. And we've already found the expected value of y sub I on a previous slide. And so if we plug that in, this expression is equal to beta 0 times the sum of the b's plus beta 1 times the sum of b sub I times x sub I. Now, it can be shown that the sum of the b's is equal to 1, and the sum of the products b sub I times x sub I going from 1 to n, is equal to 0. From these results, it follows that the mean of the sampling distribution of beta 0 hat is equal to beta 0. And so the least squares estimator beta 0 hat is unbiased as an estimator of the intercept parameter beta 0. Thinking graphically, what this means is that the sampling distribution of beta 0 hat is centered at the true value of beta 0. Next, let's derive formulas for the variance and the standard deviation of the sampling distribution of beta 0 hat. And so under the assumption of the independence of the error terms, the variance of beta 0 hat is given by the following expression. So first we will denote the variance of beta 0 hat in two ways, really. Sigma squared sub beta 0 hat, as well as var for variance of beta 0 hat. And again, under the assumption of independence of the error terms, along with properties of variance, this is equal to the sum, I going from 1 to n, of the squared b values times the variance of y sub I. So, said more precisely, the sum I going from 1 to n of b sub I squared times the variance of y sub I. Under the assumption that the error terms all have the same variance, denoted sigma squared, this simplifies to the expression sigma squared times the sum of the squared b values. Now, it can be shown that the sum of the squared b values is equal to the sum of the squared x values divided by n times s sub xx. And so it follows that the variance of the marginal sampling distribution of beta 0 hat is equal to this expression here, sigma squared times the sum of the squared x values divided by n times s sub xx. The standard error of beta 0 hat, that is, the standard deviation of the sampling distribution of beta 0 hat, is the square root of this expression. Now we will denote the standard deviation of the sampling distribution of beta 0 hat by sigma sub beta 0 hat, and also by SD for standard deviation of beta 0 hat. And that's equal to sigma times the square root of the squared x values divided by n times s sub xx. So let's put all these results together and summarize them on a single slide. In summary then, the mean, variance, and standard deviation of the sampling distribution of beta 0 hat are as follows. So mu sub beta 0 hat, the mean of the sampling distribution of beta 0 hat, is equal to beta 0 itself. And so that implies that beta 0 hat is an unbiased estimator of beta 0. The variance of beta 0 hat is equal to sigma squared times the sum of the squared x values divided by n times s sub xx. And finally, the standard error of beta 0 hat, which is the same as the standard deviation of the sampling distribution of beta 0 hat, is equal to the square root of its variance. And so sigma times the square root of the sum of the squared x values divided by n times s sub xx. Okay, next let's look at characteristics of the sampling distribution of the standardized version of beta 0 hat. And so to standardize beta 0 hat, we subtract from beta 0 hat the mean of its sampling distribution, which, as we've seen, is equal to beta 0, and we divide that difference by the standard deviation of the difference. And the standard deviation of the difference, because beta 0 is a constant, the standard deviation of the difference is just the standard deviation of beta 0 hat itself. And so that is equal to the square root of sigma squared times the sum of the squared x values divided by n times s sub xx. And so that's how we calculate the standardized version of beta 0 hat. And we're going to denote the standardized version of beta 0 hat by capital Z sub beta 0 hat. And so once we've done that, the mean of the standardized version of beta 0 hat is equal to 0. And the variance and standard deviation of the sampling distribution of the standardized version of beta 0 hat are equal to 1. Next, we're going to look at two characteristics of the joint sampling distribution of beta 0 hat and beta 1 hat. And these two characteristics are related. The first characteristic is the covariance of beta 0 hat and beta 1 hat. Using some algebra, along with the properties of covariance that we looked at back in Module 1, it can be shown that the covariance of beta 0 hat and beta 1 hat is given by the following expression. So the negative of x bar divided by s sub xx times sigma squared. Now, be careful and make sure that you don't miss that negative sign in the front. Next, let's derive a formula for the correlation of beta 0 hat and beta 1 hat. Now that we have formulas for the covariance of beta 0 and beta 1 and their variances, we can derive a formula for the correlation of beta 0 hat and beta 1 hat. Now the formula for correlation was given back in our review of distribution theory back in Module 1. And so if we plug into that formula the expressions for the covariance of beta 0 hat and beta 1 hat, along with the variances of those estimators, we get the following formula for the correlation of beta 0 hat and beta 1 hat. And so that formula is given by the negative of x bar divided by the square root of 1 over n times the sum of the squared x values. So that is what I wanted to cover in this lecture video. We've determined several important characteristics of the marginal sampling distributions of both beta 0 hat and beta 1 hat, along with some characteristics of the joint distribution of those estimators. So I'll see you in the next lecture video.